Thank you very much. I apologize for this technical, small technical delays. Well, anyway, my talk will be again about very close to integrable systems, but mainly about infinite dimensional integrable system, about so that I written as partial differential equations, more precisely about some subclass of integrable systems that I called integrable systems or integrable hierarchies. Hierarchies means family of commuting, complete family of commuting integrable systems that satisfy certain properties, and due to these properties I call them hierarchies of topological type. And I want to explain the connection of some classical stuff from the theory of integrable systems that of course is well known to experts in this area, but I wanted, but maybe less known to people who started to do integrable systems just in connection in trying to better understand the connection with the topology of the Lie-Mumford moduli spaces. What I'm going to do, so first I want to give a very brief introduction, trying to define this class of integrable hierarchies of topological type. Then I will explain this technique of the so-called dressing transformations for one particular case of integrable system that is called some classical differential equations from differential geometry. Then I will explain, this is more recent stuff just that arises when trying to understand the given tiles construction of the so-called total descendant potential. So a symplectic realization of this dressing transformation, and to add some words about quantization of these dressing transformations. Well, on this first slide, this is a kind of publicity for integrable systems. Integrable systems already is quite well established part of mathematics, both the pure mathematics and applied mathematics. It has many connections, many connections with spectral theory of linear differential operators through what is nowadays called Lax representation and so on and so forth, with the theory of infinite dimensional algebras, and the best known issues are Drinfeld Sokolov constructions of integrable hierarchies that are also very close to what I'm going to talk about. The connection to infinite dimensional Grassmannians due to Sato construction and remarkable things, what is called Katsuwakimoto construction, realization of the a kind of Hirota bilinear equation. Well, all this is well established, more recent, a little bit more recent connection. Recent means just about 20 years. Well, with respect to the about 50 years age of, almost 50-year age of the theory, modern theory of integrable systems, this is, of course, can be considered as recent. There's a connection to topology of this remarkable object topology of the Lie-Mumford moduli spaces. So moduli spaces of genus G, algebraic curve C sub G with n marked points up to holomorphic equivalences, of course. This is one of fundamental object of mathematics, and the connection between certain class of integrable systems and topology of these moduli spaces. This is one of the main challenges to be clarified. And I hope that this talk is some very small contribution towards this direction. So the discovery of this connection between topology of the Lie-Mumford moduli spaces, just to give you some first example, is due to well-known result, first conjectured by Witten, then proved by Kontsevich, Okounkov, and some other proofs. So for the case of the best known example of integrable PDE, I mean the Korteweg-de Vries equation. I already written this infinite system, well, the first three of the infinite system of commuting flows. The subscripts stand for the partial derivative. X is the space variable, one variable t, there are one space but many times, since we must have infinite number of commuting flows on the space of functions of one variable. I don't want to specify what space is. I mainly, in my talk, I will mainly deal with solutions in the class of formal power series. Okay, so this subscript u sub t0, u sub t1, sub t2 are just correspond to these commuting vector fields. Commuting means just simply that if we compute the mixed derivative, first differentiating in ti, then in tj, then the result does not depend, it's a certain differential polynomial that does not depend on the order of I and j. Very simple identity that can be easily checked for the examples, but there are some tools how to check this in general, how to construct the subsequent members of this infinite family of commuting flows. The Korteweg-de Vries equation itself, KdV, is the equation number 1, u sub t1. Also, you may observe that there is a small parameter is present, epsilon. So my equations are written as an expansion in this small parameter that physicists call this small dispersion, but in the setting, well, other physicists that invented this connection with topological field theory called the string coupling constant, and so on and so forth. But anyway, this is formal small parameters. The equations depend on the small parameter, and therefore the solution with the given initial data, and this is the initial data I'm interested in, will also depend on the small parameter. At least it will be written as formal expansion in epsilon. Let us do the following. Since all the flows commute pairwise, we can do the following. We can fix initial data, setting all times to 0, and then solve simultaneously all the infinite set of equations of the hierarchy. Solve means to write down solution in the form of series expansion, series in time, series in epsilon, of course. Initial data when all times are set to 0, u of x is equal to x. This is my particular data that is relevant for formulation of the Kontsevich-Witten statement. The statement is the following. Compute what is called in the theory of integrable hierarchies, this is called tau function. That means instead of the function u, I introduce function tau such that the second logarithmic derivative of tau up to epsilon square is just u. Well, there is some precise definition of this log tau. This is the function I needed. Since the solution is written as expansion in epsilon square, also log tau will be written as expansion of epsilon square. It begins with epsilon negative 2, of course, powers. Okay, let us write down this formal expansion. Then the statement of the Witten-Kontsevich, Okounkov, is that every term can be represented as the generated function of certain topological characteristics of the Lie-Mumford moduli spaces. Recall the moduli spaces of stable algebraic curves of G naught G with n punctures. Namely, what are the characteristics? These are intersection numbers of the so-called tautological classes. Namely, we have the following line bundle over the suitable of the Lie-Mumford compactification of these moduli spaces. The line bundle is the following. We have the curve, we have marked point. We can consider the cotangent line to the curve at the ith marked point. This is line bundle over the moduli space. Take the first chain class of this line bundle, and this is the ith since we consider the ith point. The ith tautological class in the cohomology of the Deligne-Mumford moduli space. So compute now the wedge product of this, of the powers of this, of these psi classes. Of course, the degree of this differential form must be equal to the dimension of the moduli spaces, 3g minus 3 plus n. And t's, the times of the hierarchies are just independent variables and form the generating function written here. So the claim is such a generating function, the genus G is fixed now. We change n, we perform summation over all values of n. The generating function, the term of genus G expansion in the logarithm of tau function is exactly the generating function of these psi classes. Okay? This is, in the original version, this is just a remarkable statement about one particular solution to the KDV hierarchy. This basically the idea about interval hierarchies of topological times claims that actually certain topological properties that come from the Deligne-Mumford spaces can be considered as a feature not of just one particular solution, but of any solution to the Korteweg-de Vries hierarchy, of any solution. This is more property of the system itself than the property of a particular solution. Okay? So more precisely, what is called topological recursion holds true, namely consider the partial derivative of the genus G term of log tau. These are called what physicists call genus G correlation functions of certain observables that denote the sigma. This is just notation for the left-hand side. You can just disregard this notation. For example, the U itself can be considered as the series with coefficient epsilon to 2G of 2-point correlation function of sigma 0, sigma 0. Okay? Then the topological recursion relations can be formulated in every genus. Genus 0, for example, such an identity, and genus 1 is such an identity that remarkably this identity that of course have been discovered just in the working with certain identities in the cohomology of the Deligne-Mumford moduli spaces. These identities hold true for any solution to Korteweg-de Vries hierarchy. So this is what I mean about this. This is more property of the system than the property of a solution. So the question is, what is special about Korteweg-de Vries hierarchy? What are other hierarchies? Are there some other examples? And how to classify such example? How to give how to construct them? So we can proceed in two ways. We can just study carefully the first way. Study carefully the topology of the Deligne-Mumford moduli spaces, the so-called tautological ring of the Deligne-Mumford moduli spaces, means ring generated by the psi classes, so-called psi classes, kappa classes, lambda classes, and their push forward images with respect to the so-called forgetting map. And just looking at these identities in the cohomology of the Deligne-Mumford moduli spaces, try to derive this kind of topological recursion relation, other identities for the tau function of the hierarchy, and then from this to derive the some constraints for the coefficient of my system of PDEs. Okay, this is one way, but to go along this way, one can have some good knowledge of the topology of the Deligne-Mumford moduli spaces, of course. We tried this. We begin with my collaborator Eugene Jung already many years ago. What we managed to proceed, we managed to derive some universal formula for such integrable hierarchies of topological type for at the genus 1 correction. That means the first correction with respect to small parameter epsilon square. Okay, using the already known result by Mampart, Getzler, and Witten about the genus G, maybe finally settled by Faber. Genus G universal identity in the tautological ring. Okay, but since we are not experts in topology of model spaces, then after we did this first work, we decided to change slightly, not slightly, change completely in a sense, the way of doing. So instead of studying topology and then to translate topology into some structures in differential equations, first to do some guesswork to formulate a system of axioms for a suitable class of integrable systems, and then to check that if these identities for tau functions of such integrable systems capture the identities in the Lie-Mampart moduli, in the tautological rings of the Lie-Mampart moduli spaces. So in this way, we arrived at the definition of what we call integrable hierarchies of topological type. As I will briefly now summarize what is the main point. The definition rather simple, of course. When if we want to be a little bit more precise, you have to work a little bit. It doesn't require any knowledge about topology. It requires some basic knowledge from the theory of integrable PDEs. First of all, what is the class of PDEs I'm considering? We consider a system, so this boldface U is now a vector valued function, number of components is n, and the right-hand side is written as epsilon expansion, formal epsilon expansion with certain gradation rules. So you see the leading term has degree 1 as function on the jets u sub x. Next term is a differential polynomial of degree 2, degree 3, and so on and so forth. Differential polynomial means polynomial with respect to derivatives, not with respect to u. Okay? So this is linear in the x derivatives. The next term will be linear in the second derivative and quadratic in the first derivative. So the gradation is obvious. Degree of x derivative, first derivative is 1, degree second derivative is 2, and so on and so forth. Okay? So these are the gradation rules. And polynomiality is very important points. If we extend the class of hierarchies, if we admit, say, rational functions, then the classification will be trivial in a sense. Okay, I added here another example that also for us was important, since this example of classical Toda lattice that is relevant for the theory of random matrices. In this case, you see, this is a difference equation. So if we rewrite this as a nonlinear, I would not call this even PDE, since the right-hand side is not a differential operator. But we can formally expand this difference of exponential in Taylor series in epsilon, and then we obtain a PDE of infinite order in the right-hand side. So in my expansions here, this dots means that I will allow just formal. I will work with formal expansion in epsilon. Okay. So and what is now I'm ready to give a kind of definition of integrable hierarchy of topological type. We consider just infinite family of such commuting flows, fix n, fix the infinite family. So the label I refers to the number of the flow. Okay. What it requires? It requires integrability, means that these flows must commute pairwise and satisfy a certain condition of completeness. Okay, and this is a very important point. completeness of these flows. It's quite surprising that from topology of the linear Mumford model spaces, we obtain not just commuting flows, that is just checking some identities in the cohomology ring, but we obtain a complete family of commuting flows. This is some I would say, conceptual understanding of this completeness statement is still missing from my point of view. Okay, also we can check. In certain cases, for example, as for total lattice that correspond to the intersection numbers of stable curves with values in P1. But even we discovered that this system was not complete as a simile, and we have to edit and to construct the so-called extended total lattice. Okay, so completeness is very important point. But then what we, so there's a general class, but more specific, we must require that the hierarchy must possess a tau function. Okay, this is a first restriction that doesn't hold true in general. It must be bi-Hamiltonian with suitable class of Hamiltonian structures. And it must be invariant with respect to Virasoro symmetries that act linearly onto tau function. So you see, this is all essentially what we require. Of course, you must know what it means by Hamilton and what is Virasoro algebra and Virasoro invariance. Well, but this is just technical, just to formulate this, and I will not do it today since the subject of my talk is different. My subject is mainly about dressing transformation. That is, in a sense, is more elementary stuff. I want on the slide, I want just only to clarify what I mean about integrability. So I already told you that my systems are written as formal expansion with respect to small parameter epsilon. How to deal with integrability, how to define the integrability of such system. Very simple way. Just we first look at the leading term of no epsilon at all. We require that this is a system of quasi-linear first-order system. In this case, the theory of integrability is quite simple. It has been established essentially by Sergei Tsarev many years ago and can be reduced. In this case, the theory of integrability reduced to some classical differential geometry of curvilinear orthogonal systems, and we know how to classify such system. And then so we have some infinite family of complete infinite family of first integral for the leading term. Then, to deal with the full perturbative expansion, we give the following definition of integrability. We require that the complete commutative Lie algebra first integral of the unperturbed system must admit a deformation, epsilon deformation to a complete family of first integrals for the full expansion. Quite traditional for Hamiltonian mechanics in the Poincaré style definition of integrability. It turns out that this definition is quite efficient, but still, if we want to classify all integrable hierarchies that are integrable in such a perturbative sense, this problem turns out to be quite difficult, and not many. Still are only some experimental result about first order of this perturbative analysis of integrability. So this, from my point of view, it is just an interesting problem of Hamiltonian formalism in infinite dimension. How to construct? Let us assume that we know how to construct the leading term integrable quasi-linear first-order system using this Tsarev construction, for example. How to construct an integral perturbation? The first way is just fairly trivial. Let us consider such a substitution, kind of what we call a generalized Muir transformation. Instead of dependent variable u, I consider new dependent variable u. That is written as just formal epsilon expansion, such that this term f1 is linear in the first derivative term, f2 is linear in the first quadratic in the second. So as before, this, the term of order k must be differential polynomial of degree k. Do a substitution and rewrite the original vector field in new coordinates. Well, since the original vector field was integrable, it will remain integrable also in new coordinates. And in this way, we obtain, of course, an integrable perturbation in all orders. Such perturbations are trivial. Of course, we are not interested. And all examples like KDV, nonlinear Schrödinger, and so on and so forth are not trivial. But we can improve the trick. Do such a substitution that is not polynomial in jets, v sub x, vxx, and so on, but is rational in jets. Okay? Requiring, of course, that after substitution and rewriting, all the denominators must cancel. This is a miracle of the theory of integrable systems, that such a substitution always exists. This is already a theorem. Okay, and however, the question how to find such a substitution. Okay, this is an example for the KdV, the first few terms. Here you can see log, but there is a second derivative of log. When you compute the second derivative, you obtain some rational functions in jets. So order epsilon square correction, epsilon to the 4 correction, and then so on and so forth. Quite complicated rational expression. It is not that easy even to check that after substitution, term by term, that you obtain again. If you apply, for example, to the Hopf, perhaps I will try to use this fancy device. You apply to, say, Hopf equation v sub x, such a substitution, v goes to u. Then to check that what you obtain Korteweg-de-Vries equation. All the denominators will disappear. This is a magical identities. Oops. That in this case one can prove, but the question how to produce all such substitution, how to classify them. Okay, so the construction in general of integrable hierarchies of topological type that we develop with Eugen Jung is based on the so-called 3G minus 2 lemma that says is a little bit strange property of integrable hierarchies that also was discovered in this stuff with topology of the Riemann spaces is the following. Let me return to this epsilon expansion of log tau. Then the claim is the following. Every term in this epsilon expansion that in principle is function of infinite number of times, starting from f1, f2, and so on and so forth, can be written as functions on v, where v is logarithmic derivative of the leading term. That means this is a solution to the dispersionless system, to the first order quasi-linear system, to the unperturbed system. Okay? Written, but the terms of order g that first was function of infinite number of times. Now it will depend only on finite number of jets. Such ansatz was first conjectured by Iguchi and his collaborators in the 90s. Then Iguchi and Getzler proved this from vanishing of certain powers of tautological classes on the Riemann space. In our setting with Eugen Jung, this 3G minus 2 lemma follows from the existence of a Hamiltonian structure. Okay. Anyway, this expression, well, let me return for the moment to the previous slide. What is about 3G minus 2 lemma? You see, this is second derivative, that means the second logarithmic derivative of tau. So this is a one term, is function of v sub x. This is f and 3g minus 2 for g is equal to 1, 3g minus 2 is equal to 1, of course. So this depends on the field jet. This is the F2 that depends on jets up to fourth order. 3g minus 2 in this case is equal to 4, and so on and so forth. Okay? This is the property. And we use this property as in the construction. We first construct this expansion in the form of 3g using the 3g minus 2 lemma, and then we do a substitution, taking logarithmic derivative, and T0 is the so-called primary time of my integrable hierarchy. In this way, what we were able to prove that many integrable well-known integrable hierarchies belong to this class of integrable hierarchies of topological type, like Korteweg de Vries, nonlinear Schrödinger, Toda, Drinfeld Sokolov hierarchies for simply Lacely algebras. But there are much more integrable hierarchies. So in this way, the point is not just to identify which of the known integrable hierarchies are good and which are less good, but also to construct new hierarchies. And this also will be the main point of the rest of my talk. Main idea, now I will switch to dressing transformation. I'm just coming to dressing transformation, and I begin with some elementary classical differential geometry. That is the so-called Darboux-Yegorov system. This is the system for n times n symmetric of diagonal matrix gamma. So of diagonal means the zeros on the diagonal. And gamma j, the entries of this matrix are functions on n variables u1, un, on u. Okay, this is the full set of equations. I will explain on the next slide what is the meaning in differential geometry of the setting. The theory of the so-called Frobenius manifold is very closely related, of semi-simple Frobenius manifold, closely related to this Darboux-Yegorov system. One has to add just one scaling reduction. So must require that gammas as functions of u must be homogeneous function of degree -1. It's very simple system, and you know, in the people in the theory of integrable system like very much the name master equation. So more or less every expert in integrable system who works in this area for a few years has his own master equation. So this is my master equation. The point is I want to derive to classify integrable hierarchies of topological type by solutions to this master equation, by solutions to the Darboux-Yegorov system. So to this point, I have to, first of all, tell you some way how to generate solutions. Okay, this is the point about classical dressing transformations, and then how to associate integrable hierarchy of topological type to every solution. Well, the word every is a little bit, maybe too much, say every. I will tell you about some class of solutions. Actually, in our paper with Eugene Zhang, we mainly work with the solutions satisfy this scaling reduction that come from Frobenius manifold, and this main class, all known classes belong to this. But I want actually to forget about this scaling reduction. I want just to work with the original Darboux-Yegorov system, and when I want to produce some class of solutions to this system, and then to associate with them integrable hierarchy of topological type. So geometrical meaning of this Darboux-Yegorov equation is the following. We consider so-called Yegorov curvilinear orthogonal coordinate. So that means what is curvilinear orthogonal coordinate? This is just metric Riemannian or pseudo-Riemannian in n-dimensional space that is diagonal in certain coordinates u and has curvature 0. So that means in some different coordinates the metric can become Euclidean or pseudo-Euclidean. Okay? Then the subclass of Yegorov curvilinear orthogonal coordinates are those coordinates such that the coefficients of the metric, the so-called squares of Lemay coefficients, admit a potential. Exists some function V that the ith diagonal entry is the partial derivative of this potential. Equivalently, this condition exactly means the symmetry of the so-called rotation coefficients. So this is the definition of rotation coefficients. So this matrix must be symmetric. That's it. Then if you spell out the equations for vanishing of the curvature of such of the Riemann curvature tensor of such a diagonal metric, then you arrive at the Darboux-Yegorov equation on the previous slide. Okay. My notations are slightly non-standard. Sorry about that. So usually in the books in differential geometry, rotation coefficients are determined not by gamma, by beta, but for technical reasons, since in the tech version, in the old version of tech when I started to work about this, there existed capital gamma but did not exist capital beta, so I had to switch from beta to gamma. Anyway, this is the same. Integrability of the Darboux-Yegorov system. This is something that I observed many years ago. It's very elementary. So this is the so-called zero curvature. Now I use the word zero curvature in different sense. Zero curvature in the sense of the theory of integrable system, a kind of analog of Lax representation. So the Darboux-Yegorov system is equivalent to commutativity of this linear differential operator, vanishing of the curvature of this connection depending on the so-called spectral parameter Z and on the trivial bundle over the U space. Here, capital E sub I is a matrix unit. V is commutator of gamma with EI, so it's a very simple matrix. Since gamma was symmetric, V will be anti-symmetric. This is important to remember, anti-symmetry. And the following lemma is essentially about solutions to a system of linear commutative system of linear PDE. Says the following: given a solution gamma of U to the Darboux-Yegorov system that is analytic on some ball in the n-dimensional space, then there exists a wave function, this matrix valued function phi, that is analytic on this ball and analytic also in Z, at least on some disk of positive radius, more precisely analytic on such a cross product. Moreover, because of this anti-symmetry of V, we can normalize this wave function in such a way by this condition: phi transpose U of minus Z times phi of U Z must be equal to the identity matrix. I will work always with such normalized wave function. Okay. Now we'll explain how to obtain mini solution to the Darboux-Yegorov system started from the given solution. This is the old idea of dressing transformation. So started from, actually I will always work with the pair, the solution to the Darboux-Yegorov system and the normalized wave function, gamma and phi. Starting from gamma and phi, I will derive in U gamma tilde, phi tilde. What is the data of my transformation? First of all, I will assume that the radius of convergence in Z is number rho greater than 1. We can always achieve this doing suitable rescaling. The construction is the following. Given a matrix valued function G of Z, matrix of the same size, n times n, analytic on some neighborhood of the unit circle, okay, and satisfying the following, like orthogonality condition. By orthogonality, we have to change sign. G of Z does not depend on U. We consider the following Riemann-Hilbert problem. Consider phi, G phi inverse, a function on the unit circle. We want to factorize this function as a product of two matrix valued function. One is analytic inside the unit circle, Another is analytic outside of the unit circle. And if such a factorization exists, we can uniquely normalize it by the following normalization condition. It's G infinity. The infinite points must be equal to the identity matrix. Of course, there exists the problem of such factorization is the problem of analytic trivialization of certain vector bundle of the Riemann sphere. So in the right-hand side, we have the transition function of this vector bundle over the Riemann sphere that depends also analytically on this parameter u. So we have what is people call usually Riemann-Hilbert problem with parameters. And so it is well known that result essentially due to Bolle-Bruch about this Riemann-Hilbert problem with parameters, that if such a trivialization exists for a given point u0, it does exist and is in some neighborhood of u0 and depends analytically on u. Okay? So because of unicity, this factor G0, G infinity will depend analytically on u. Then is the formula of the dressing transformation. Phi tilde is G0 times phi. Gamma tilde is gamma plus the off-diagonal part of this limit. The claim is this is another solution to the same Darboux-Egorov system and another wave function, another normalized wave function. Okay? This is the construction. I do not remember even who was the first who. Of course, this is written in the textbook. This is nothing new in this construction. And this is basically the way how to prove, how to we have to differentiate the definition of G0, G infinity that I wrote before, differentiate with respect to ui, and that after some simple transformation we obtain the following equality of these two expressions. I forgot to say that the matrix G0, the analytic factors, analytic inside, analytic outside, must be not degenerative on this domain. Not degenerate because of this we can invert. Then what we have, this expression that I denote as script ui, the left-hand side is analytic inside the unit circle, the right-hand side is analytic outside the unit circle. So that means it must be analytic everywhere on the complex plane. It suffices to check what happens with this function at infinity. And due to my normalization, if you look here, it is easy to guess that infinity, it has just at most simple pole with the leading coefficient u sub I. So that means that this is just linear matrix valued function in Z. And if we just rewrite this for this function phi tilde, this is a reminder what is phi tilde, you obtain again, it will satisfy this equation of the flat connection. Okay, so we obtain another flat connection. We know that commutativity of this, compatibility of this linear system is exactly the Darboux-Egorov system. We obtain this class of transformation. Analyticity is important, of course. And this I want to stress this point. Without analyticity, it becomes a little bit senseless. So one more remark that about the product. This is a kind of group. Of course, we must require that for every factor G1, G2, the Riemann-Hilbert problem admits a solution. But then, under this assumption, it's easy to check that to the product of the matrices defined on the unit circle, it corresponds to the superposition of the dressing transformation. Let me consider also the infinitesimal version where the matrix capital G is close to identity. In this case, there is no problem with the solvability of the Riemann-Hilbert problem. That in this case, all vector bundles with the transition function close to identity, of course, will be analytically trivial. In this case, we obtain an action of the Lie algebra we obtain Lie algebra of dressing transformation. So the matrix G is just the element of the Lie algebra. So we consider all the formula in the linear approximation in G. The matrix G small must satisfy such, instead of orthogonality type constraint, it must satisfy this antisymmetry type constraint. So in this case, the Riemann-Hilbert problem in the linear approximation can be solved elementary. We have to consider the positive means analytic inside part of such a product and analytic outside and vanishing in infinity part, sub plus, sub minus. And immediately we obtain the formula for explicit formula for the action of the Lie algebra of addressing transformations on the gamma matrix and on the phi matrix. This is strangely, I wasn't able to find this formula for the Lie algebra of addressing transformation in the literature, but this is absolutely trivial. Now I have to convince you that indeed from this family of solutions to the Riemann-Hilbert system, how to explain the recipe how to produce integrable hierarchies of topological type. Since you may remember the crucial point was in the construction of tau function, I will be able only to explain how to construct the tau function. Let us do the following. We want to construct this expansion, Fg. I will first construct F0, and then I will explain how to construct the higher correction. Consider the following auxiliary space of formal vectors, well, maybe convergent vector series, so convergent outside the unit circle, with vector valued coefficients, Q. Qm is just for every m is a vector in the same Cn. So there are no constant terms in this H minus. And define the residue map. This B is my ball in the Cn space. H minus, this is the space of vector valued formal series. And the residue map is just indeed residue of the product. The wave function matrix multiplied by this vector and then integrated over the unit circle. This is residue as function of u of the point in the Cn in the neighborhood of u0 and on q of this function analytic outside the unit circle. Define the Hodograph variety that by taking the zero level zero value level surface of this residue map. So equation residue is equal to 0. This equation for u and q. This is some variety in the infinite dimensional space, well, finite dimensional space, this ball times infinite dimensional space of analytic functions outside the circle. Okay, in general, singular variety, but it is easy to identify the regular points of this variety. U0, Q0 is regular if and only if such integrals for every j, if every components of this vector must not vanish. Okay, it is easy to check that regular points do exist. Now I will consider I am able to consider F0. This will be the following, consider the following quadratic functional on H minus, this is the definition of omega, restricted on this Hodograph variety. Okay. Well, phi is the same wave function. You may remember that it satisfies certain normalization. Due to the normalization, the difference is divisible by z plus w. So this expansion is analytic in z and w. So the double integral is well defined. The crucial observation for the construction is the following, due to Giventhal. Is the geometric meaning of this F0 function. That this F0 is the generating function of certain Lagrangian submanifold in a suitable infinite dimensional symplectic space. Okay. Now I will explain what is the Lagrangian manifold, but first I will explain what is the symplectic space, the Giventhal symplectic space. So consider the infinite dimensional space script h, that vector valued function on a unit circle. Again, function on unit circle, always I consider analytic on some neighborhood of the unit circle. This is the symplectic structure on the Giventhal space. Okay. Well, these angle brackets mean the standard Euclidean inner product on Cn, sum of squares. Not Hermitian, but sum of squares inner product. Okay? Well, why it is symplectic? Well, first of all, it's easy to see that this bilinear form is antisymmetric. If we interchange f at g, okay, you have to replace z by minus z, and the integral will change sign. Why this bilinear form is a non-degenerate one? Well, it is one can easily produce a natural polarization. Two complementary Lagrangian subspaces. This subspace H plus of functions analytic inside, H minus analytic outside. H minus the same notation I used before. Okay, so H plus will be momenta for me. H minus will be the coordinates. Okay, so what is the Lagrangian submanifold, so-called given-type Lagrangian cone? Script L, it is a subset PQ in the given-type symplectic space, where P of Z is given by the following formula. And the lemma is that the function f0 is exactly the generating function of this Lagrangian submanifold near a regular point. There are also singular point of this Lagrangian submanifold, but I will not enter into details about the singularities. The main point that I want to explain in the remaining few minutes of my talk, I started later. Okay. The main point is the small addition to the classical stuff about the dressing transformation is the following: is the symplectic realization of this dressing transformation. This is the theorem. Is the following: we have for every dressing transformation we have a deformation of solution to the Darboux-Egorov system, deformation of phi, deformation of hodograph variety, therefore deformation of the given Lagrangian cone. The claim is that this deformation is a canonical transformation, is generated by symplectomorphism. More precisely, this is the infinitesimal version. I consider the infinitesimal symplectic infinitesimal dressing transformation generated by the given function G, matrix valued function G small, satisfying certain skew symmetry construction. The following: consider the following quadratic functional, quadratic Hamiltonian on the given symplectic space. Consider infinitesimal symplectomorphism generated by this quadratic Hamiltonian. Okay? Then the claim is this infinitesimal symplectomorphism generates my dressing transformation, infinitesimal action of my dressing transformation onto given Lagrangian cone. Okay? So this all about the, I would say, the general zero part of my expansion of log tau of my integral hierarchy of topological type. The proof easily follows from the formula for the variation of this matrix omega. This is the explicit formula for the variation, that in some form, not exactly this form, it appeared already in the works by Yinping Li and Sergei Shadrin and his collaborators, but it is different, however, since in their form, they essentially what they work in, just analyzing their formula that look completely differently from those. Analyzing their formula, since the symplectomorphism not only deforms the Lagrangian cone, it changes, of course, the regular point if we want to consider the behavior of the generating function of this Lagrangian cone. We first have expansion of the generating function near one regular point of the symplectomorphism. We will have expansion near another regular point. If we want to fix this regular point, fix what physicists call dilaton shift, then we have to add some additional transformation, and this is just important to compare my formula with those by Li and Shadrin. Okay. So then to extension to higher general. This is essentially due to the following remarkable construction, first perhaps observed by Chekhov and then in general by Giventhal, is we have to use the suitable quantization procedure, considering epsilon square parameter as a Planck constant. So then we quantizing Lagrangian submanifold, and this is the semi-classical state exponential of 1 over h bar f0. 1 is usually f0 is called s, the action function. Okay, exponential of s over h bar. We have to quantize. We arrive at the quantum state that exactly my full tau function. And quantizing the dressing transformation, considering them as symplectomorphism, we obtain a quantum canonical transformation that transforms one quantum state to another one. What remains to do it remains to apply this quantum canonical transformation to something known. And we take the Kontsevich-Witten function, more precisely the Cartesian product of n copies of Kontsevich-Witten function, as Chekhov and Giventhal did, and then apply this quantum canonical transformation. The only thing to be checked about this 3J minus 2 lemma, why this is the case. Well, you have to quantize essentially exponential of quadratic Hamiltonian. Quadratic Hamiltonian after the quantization will consist of 3 parts. The part q times q, that is just operator multiplication by quadratic form. P times q, that is a linear operator, that's linear change of coordinates in the q space. And then P times P, that is second order linear differential operator. We must be able to compute exponential of the of linear second order differential operator in order to perform quantization. The question is, of course, our system, we are quantizing a system with infinite number of degrees of freedom. So we have essentially to compute time one shift along the trajectories of a kind of parabolic, of infinite dimensional parabolic equation. So delta is some second order linear differential operator of infinite dimensional. Okay. The point is that we have this present of this epsilon square parameter, and also the Kontsevich-Witten function also written exponential of some expansion 1 over epsilon term, and the remaining is regular expansion epsilon square. Then the following formula is crucial in justifying the 3J minus 2 lemma that says that the solution to this parabolic expansion, or a parabolic equation with such type of initial data, that means the following asymptotic expansion, okay, where one has to replace the variable x by the new variable y that is related in such a case. Using this asymptotic expansion, one can easily justify and to prove that the function log tau we construct in this way does admit this 3J minus 2 expansion. Then we can perform all the tricks and produce integrable hierarchy of topological type. The last slide, I want to return to some much more simple way to discussing one important point of all this program. What kind of integrable hierarchies we obtain in this way using this transformation. Whether this action is transitive on the space of solutions to the Rabou-Egorov system. And in order to clarify this point, I consider the following very simple, perform the following simple exercise. Consider the n is equal to 2 case, and consider the dressing of a trivial solution. Gamma is equal to 0, then the wave function is just exponential. And I consider the infinite epsilon dressing transformation. The matrix, 2 by 2 matrix G of Z must have such a form. This is the diagonal entries are odd function. The off diagonal just must be related to such a form. The important part of a dressing transformation depends only on the negative part of G12. Let me represent the negative part in the following way, where f is written as function of 1 over z. Where f is such a function, since G12 must be analytic in some neighborhood of the circle, the negative part, this f of z is analytic on some disk near the origin. Then just one line computation says that this rotation coefficients of my new Darboux-Yegorov metric, gamma 1, 2, is given by the following formula, where BF is the so-called Borel transform of the function f. Borel transform. So instead of what is Borel transform, this is the series we insert factorials in the denominator. This is a well-known trick to perform summation of divergent series. My series was convergent. My policy was convergent. So what? It means that easy to prove that this Borel transform is an entire function. We do not obtain everything. What we obtain only those Yegorov metrics that are entire functions. So, for example, if we want for n is equal to 2 Frobenius manifold, then gamma 1, 2, of course, is function only that depends only on the difference, since the sum, if you remember the equation, they imply that it depends on the difference. In the theory of Frobenius manifold, it must be homogeneous function of degree -1. So what is it? It is equal, it is constant, divided over U1 minus U2. So it can never be obtained by dressing transformation. It's a different class of solution. So the group of dressing transformation acts transversally on the subset of Frobenius manifold. So that means that also we indeed produce some new integral hierarchies. This is a good point. And to the best of my knowledge, none of these integral hierarchies that can be obtained by dressing transformation have been studied before. But we cannot cover some important examples. So that to cover these important examples, one must use more advanced trick in the theory of this Riemann-Hilbert problem, isomodromy deformations, what we used before in the theory of Frobenius manifold. I think this is enough. Thank you.